Start recording. Okay. Did you want me to summarize that? Okay, so if we have a polar molecule, let's say we have something that can hydrogen bond, you'll have three types of IMFs present. We'll have LDFs, we'll have dipole-dipole, and we'll have hydrogen bonding. Of those three, hydrogen bonding is the strongest type, so that's going to be your dominant intermolecular force. So that's going to affect the properties the most. Those properties would be a high boiling point because it requires more energy to break the molecules apart. A low vapor pressure because vapor pressure, the stronger the IMFs in the liquid, the fewer gas particles can escape into the gas portion up here. And the fewer gas molecules there are, the lower the vapor pressure. So if we have something that has strong IMFs, the vapor pressure will be low. Now, if we have weaker IMFs, more molecules can escape to the gas phase, so the vapor pressure will be bigger. So we'll have more gas molecules in the same amount of space. With a nonpolar molecule like CO2, you're only going to have LDFs. So if you only have one thing, it has to be the dominant force present. And because it's a pretty weak force, especially for a small molecule like CO2, it does not have a lot of electrons. It is not very polarizable. In that case, this is going to have a low boiling point because it doesn't take much energy to break the bonds. And it will have a high vapor pressure. Is good? Okay. Two main factors that affect the strength of London dispersion forces. This is page 75 now. One of them is polarizability. And what affects polarizability? Polarizability depends on what? The size, but more specifically, not just size, but number of electrons. Now, I will say that very often you will be given the molar mass, not the number of electrons. So if you are given molar mass, you need to be able to make the leap and say, if I have a larger molar mass, I will have a larger number of electrons. Okay? They never want you to explain, oh, I have more London dispersion forces here because this has a higher molar mass. That's not why. It's because a higher molar mass means that you also have a larger number of electrons. Therefore, it's more polarizable. And therefore, the LDFs are greater. So you can see fluorine has 2 times 9 is 18 electrons, and its boiling point is negative 188 Celsius. Iodine has 2 times 53, which is, what's 2 times 53? 106 electrons, and its boiling point is positive 114. So it makes a huge difference here, yes? Iodine has so many more electrons, and so the intermolecular forces are much stronger. The LDFs are stronger. Okay, now if you're wondering what that looks like, here is fluorine with its 9 electrons, and here is iodine with its 106. I think I actually did just 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think I did 53 on the other side because it got too crowded if I doubled them. Yes? But I probably did count. If you have nothing better to do one day, you can count in the iodine, see if I put 53 in there. Okay, I probably did. I'm a little OCD that way. So what happens is that if you take a look, the one with the larger electron cloud, more electrons, can be more negative and more positive than fluorine, because fluorine simply doesn't have as many electrons to go to one side. Is good? So that's the first thing that can affect LDFs. Probably you already knew that because we kind of covered that on our previous test about IMFs. Okay. Quick way to check the number of electrons, check the molar masses, but molar mass isn't the real reason. Okay. Factor number 2. What is it? So we have neopentane. Pentane is C. Neopentane looks like this. It is C5H12. That's neopentane. Over on our other side, we have N-pentane. Okay, and it is C1, 2, 3, 4, 5. So its formula is C5H12. So what can you say about the number of electrons in each of these? They are the same because they are actually, they have the same molecular formula. What would we call molecules like this that have the same molecular formula but different structural formulas? These are isomers. Okay. Boiling point of neopentane is 282.7 Kelvin. That's why it's such a big number. And N-pentane is 309.4 Kelvin. So are the London dispersion forces the same in these two molecules that have the same number of electrons? Or are they different? Are the London dispersion forces the same strength? One boils at 300 degrees, 310, and one boils at 282. Are the London dispersion forces the same? No, because this one boils at a higher temperature, therefore the LDFs are stronger. And over here, the LDFs are weaker because our boiling point is higher. So what is making the difference between these two? It's not the number of electrons. Take a look at the pictures and see if you can figure out what might be happening. Yeah? Intermolecular forces, yep. Okay, so there we've got the LDFs are intermolecular forces here, the London dispersion forces. Yeah. A little bit. You're almost on the right track. It does have to do with the shape. I want you to look, I've drawn two molecules. I've drawn, like I say it like I drew these things. I have clip arted these things one beside each other. If you had to draw your LDFs like this, whoops. You know how I usually draw them like that? How would you draw it here? In between. So like this. Or would you draw it like that? Yeah. Yeah, you have a greater surface that comes in contact. So if you have a long, skinny molecule, you have a greater surface area. So it's as though, imagine that you had Velcro on a soccer ball. Yes? And you've got one soccer ball, and you've got Velcro, and you've got a second soccer ball with Velcro. Compare that with if you had a board with Velcro and another board with Velcro. Which one's going to be harder to get apart? The board, because it's just stuck in more places. Yeah, you've got the forces happening in more places. So if you have things of similar molecular weight, but one is more than the other, it probably means that the longer, skinnier one has more LDFs because they've got more points of contact. Okay, and I think we talk about that here. We have an increased surface area in N-pentane. You have more points of contact, and here you have fewer points of contact. Is good? Okay. Okay. Now, finally, we're going to take a look at this one here. Dipole-dipole interactions or dispersion forces. If we have comparable size and shape. So let's say that we had which of those two would have a higher boiling point and why? They're about the same size, they're about the same shape, they have about the same number of electrons. Yeah. The one with, yeah, the one where we have oxygen, because if we have oxygen, what can we do? Number one, we have a dipole, right? We're pointing towards the oxygen, and I know this looks like they cancel, but they don't really, because the oxygen is really like this. Everything's always at angles, okay? Like when you see carbons like this, they're actually yeah? And the oxygen's actually like that, and we have a C here, and we have an H here, and we have a C here. Okay, so we've got like that. Okay, so it's polar. Also, we've got an O attached to an H, so what kind of bonds can we form?
H bonds.
H bonds, hydrogen bonds. So what's going to be more important in determining the boiling point? It's going to be the H bonds. Yes, the fact that this thing has one has dipole-dipole and one does not, that's what determines which one has the higher boiling point. But if you have one molecule which is much larger than the other, so let's say that we had I'm not going to draw all my H's, okay? Everything that's there, those all have H's on the end, okay? First of all, the molecule on the left, polar or nonpolar? Polar. Molecule on the right, polar or nonpolar? Nonpolar. What if I told you this has a higher boiling point? Oh, why?
Because it has a greater surface area.
It has a very large surface area and a lot of electrons. And that allows, even though normally LDFs are weaker, you can end up with LDFs that are stronger. If you think about butter, okay, butter's a nonpolar molecule. Okay, butter molecules are nonpolar. But when you put them together, they're a solid. Yes? Unlike vinegar, which is polar, and it is a liquid at room temperature. And that's because butter molecules are really long and skinny, and the LDFs manage to be like so sticky that they are hard to come apart at room temperature. Does that make sense? Okay. So if we have a high enough surface area and a lot of electrons, I don't know why I made that one word, I'm so sorry, allow the LDFs to be very strong. Okay, so they could even be stronger than H bonds under particular conditions. Is good? Okay. And I think that's it for this thing. Yes, we don't need to talk about that anymore. I did also want to take a quick look at 12.2c and make sure. Are we good? We're not going to do this because I think a lot of you have a good intuition about what molecules are polar or nonpolar. So this is on page 28. 28. If you can look at this molecule and tell me whether it's polar or nonpolar, you're probably good to go. Is that polar or nonpolar?
Polar.
Polar. How about CH4? 28. How about CH4? Polar or nonpolar? Nonpolar. It's symmetrical. Yes? Which of these ones are polar and which are nonpolar? Bent is polar. Trigonal planar is nonpolar. Tetrahedral is symmetrical. Nonpolar. Yeah. Huh. Okay. So you don't want to do like a 2D symmetry. Okay. Because this would be bilateral symmetry. Okay. Where you have it reflects across itself. But if you cut it this way, no. Right? It doesn't reflect across the XY or across the Y axis. Yeah. So that is asymmetrical. But this one, it's got the same forces pulling and canceling each other out. Mostly. Okay. If you're not getting it, if you're looking at this and you're like, I don't get it, I don't get why this one is polar and this one is nonpolar, then I'm going to ask you along the way to please watch this video. Okay? Because it goes through a whole bunch of examples. Okay? How about linear? Here, polar or nonpolar? Nonpolar. There's like a whole bunch of adding of vectors and things. Okay. Let's see. Do we have any questions on here? Nope. Polar or nonpolar, a shortcut. You can learn the shortcut. If you have different terminal atoms or you have lone pairs of electrons on the central atom, it will be polar, except linear. When you have 5 electron domains, I think you're better off just kind of going intuitively, to be honest. Or 6 electron domains. Or if you have square planar. All of these ones are non-polar. And if you're really like, I'm not getting it, you can learn to draw the net dipole moments. I can teach you if you would like. Would you like? Or do you feel like your time would be better used doing some review? I feel like your time would be better used doing some review. Okay, good. So you guys are going to, and I also wanted to mention that this, it's in in book 11, our bonding book, valence bond theory and hybridization. You don't need to know anything other than whether it's SP, SP2, or SP3. You don't need to know how it happens because AP will not ask you how it happens. If you're interested, come talk to me. I can explain it to you. All right? But AP doesn't care. There you go. All right? Review for the rest of class? Okay. Good stuff. And if you want one of these, this is what I was doing on the weekend. It covers intermolecular forces, molecular polarity, covalent network solids, molecular solids, metallic solids, effects of bonding and IMFs on properties. Everyone in period 1 took one, so you might as well take one. There you go. You don't end up using it, it's okay.